This work is done in collaboration with a number of colleagues. My colleagues from Barcelona, people here at the Department of Material Science, colleagues at the Diamond Light Source, which is a synchrotron in the UK, and then colleagues also in the UK, in the Institute of Magnetism, and in Mexico, in the Instituto Potosino de Investigación. So I guess the interest in, and I guess is the interest for the whole session of these so-called magnetic functional materials or magnetic multifunctional materials is that they tend to have strong coupling between multiple properties. So this could be, let's say, between structural and magnetic properties, and then you have magnetic memory effects, magnetic superelasticity. You can have coupling sometimes directly or indirectly between the magnetic and electrical properties, and then you have magnetoelectric effects, where you can control polarization with a magnetic field or magnetization with an electric field. And then you also have materials that have a strong coupling between, let's say, the magnetic and the thermal properties. So you have magnetocaloric effects, or let's say the structural and the thermal properties. So you can have elastocaloric or barocaloric effects. So they are very interesting for a number of potential applications. They are also interesting from the physics and the material science point of view. And the commonality that they have is that they tend to show these large effects when they are close to a phase transition, because it's when you are close to a phase transition where you can expect to modify the properties of the materials by a large amount applying an external field. And this is where normally interest lies in terms of applications and also science. So today I'm going to be talking about two different sets of materials. The two of them are, well, I mean, especially the first one is a classical magnetocaloric material. It's a manganite of lanthanum strontium manganese oxide, so this one here, which you can actually grow on top of a ferroelectric substrate because these two materials are perovskites, so they have the same structure. So it's very easy to grow them one on top of each other. And when you do that, basically you have a combination of a magnetic material with a strong structural coupling and a ferroelectric material. So you can expect to have magnetoelectric effect. So this is an example of an extrinsic multiferrite material that is strangulated. And then in the last part of the talk, I'm going to be focusing on the effect of isotropic stress, in this case it's a hydrostatic pressure, on the properties of manganese, basically bottom doped manganese collagen nanoalloys, which is a very well-known magnetocaloric compound as well. And just for the sake of simplicity, I will refer very often to the manganite system as LSMO here, so I don't have to say that for the composition of the time. Right, so when you grow manganites on ferroelectric substrates, because the strain coupling is good, you can actually create what are called extrinsic magnetostructural transitions. So in effect, what happens is that when the substrate has a phase transition, and in the case of barium titanate, which is a very well-known ferroelectric, what happens is that at very high temperatures is cubic, then at room temperature is tetragonal, and then on cooling down, below room temperature it becomes orthorhombic, and then below 200 kelvins it becomes rotohedral. And every time that the barium titanate changes phase, so the strain coupling with the manganite film on top, you can change the magnetization, you can control it. So if you measure magnetization as a function of temperature of this film, in this case LSMO, which is shown here with the square data, and you also look at another compound, which is LCMO. So this will be the calcium manganite, which has a stronger magnetostructural coupling. You can see that around 200 Kelvin, where the transition in the substrate between orthorhombic and rhombohedral phase happens, there are big jumps in the magnetization, which is a signature of this extrinsic magnetostructural transition. We are changing at the same time structure and magnetic ordering. And these actually give you large values of the temperature derivative of magnetization, which is a signature of large caloric effects, large magnetic caloric effects. So this is something that is, I mean, it points to you that you can use these materials for that application. But then if you look into a bit more detail, if you do magnetization as a function of magnetic field measurements just before and after the transition, you can see that the two materials actually behave quite differently. in the case of LCMO, you can see that there is a change in magnetization across the transition, so this will point out to an entropy change. Whereas in the case of LSMO, you can see that the total magnetization doesn't really change, but there is a change in anisotropy. And this is going to, this points you out in the direction of having good magnetizing effects. And indeed, actually, for the calcium manganite, we actually did this study a few years ago, where we looked at this phase transition with a number of techniques. So this slide summarizes all the techniques that we use. So on the left, these are magnetic images done by PIN reflex MCD contrast, which we run on the synchrotron here in the UK. And just if you concentrate in the two images in the middle, you can see that when you go from the high temperature phase to the low temperature phase, what you have is an increase in the amount of ferromagnetic phase. So here the paramagnetic phase is black and the ferromagnetic phase is white. LCMO is known to have phase separation, and this phase separation is modified by strain and by stress. So what happens is that in the high temperature phase, the LCMO is quite phase separated into ferromagnetic and paramagnetic regions, and then when you drive the transition in the substrate, the film becomes mostly ferromagnetic, and this gives you this big increase in magnetization across the transition. You can basically get the same data using ferromagnetic resonance, and then you can calculate the caloric response using the Maxwell relationships. And interestingly, what you see is that near this extrinsic magnetostructural transition that is driven by strain coupling between the substrate and the film, you can get magnetocaloric effects that are order of magnitude larger than the intrinsic caloric effects that happen near the point of the film itself. Of course, this peak is very narrow, so the applications are not going to do anything. But from the science point of view, it's an interesting example of how you can use stress to tune the properties of existing magnetocaloric materials and increase the performance by, in this case, now development. Then what we've done after is focusing on the other sample, on the LSMO, in order to study these changes in anisotropy. And just to give you a bit more detail, so these films in particular are 55 nanometer thick, and they are grown on 0.5 millimeter barium titanate substrates. They are grown by pulse laser deposition. So this is a picture of the chamber. So what you do is you have your material target, and then you hit it with a very high fluence laser, so you can basically vaporize the target material, and then you can deposit in a very controlled manner in the substrate. So you can make these epitaxial films that have very good strain coupling. And then when you measure, or when you look at this sample at room temperature, as I said, barium titanate is in a tetragonal phase. So if you perform X-rays, what you see is that in effect, effectively, BTO is tetragonal, so you have these two peaks corresponding of the direction of the z-axis, if it's in plane or out of plane. And then you also see the peak of the film, of SNO, which is pretty broad, because the strain mismatch between the substrate and the film is quite large, so you have relaxation. If you go further, then you can do actually magnetic imaging. So this is similar to the images that I showed you before, but then instead of looking at magnitude only, we are going to look at magnitude and direction. So this image is an image of these samples at room temperature. And you can see that there are two distinct regions. So there are regions like this one here, where the magnetization is either pointing right or left. And then there are regions like this one here, where the magnetization is mostly pointing down or up. And you can see that this pattern repeats. So you have this kind of microstructure, which is unusual for LSMO, because LSMO on its own will not show this microstructure and this local magnetic anisotropy. So if you want to correlate this with the structural information that we have on the substrate, as I said, you need to look again at the X-rays. So you see that you have these two different regions where the z-axis is either in plane or out of plane. And this z-axis, by the way, is the direction of the relative polarization in the material. And you can see from these peaks that there is a majority of C domains in plane, because you see this peak, which corresponds to the z-axis in plane has much higher intensity in the X-rays. So what we know from the X-rays is that we can expect a microstructure that looks a bit like this. So this is a picture that is basically constructed using optical microscopy with birefringence. And if you have regions in the substrate where the polarization is in plane, what happens is that the material makes this microstructure of alternating domains where the polarization is pointing right or down or right and down. And it does this in order to minimize the strain energy associated with this configuration. So if this is what you expect to see at the surface of the substrate, then let's see how do we expect the polarization and the magnetization to look. LSMO has positive magnetostructure, which means that if you take it and then you strain it, so you apply strain or stress in one direction, the magnetization is going to rotate and is going to align with the direction of the strain. So from that, what we know is that in, let's say, this region here in this image, where the magnetization is either right or left, we know that this corresponds to a region in the substrate where the corrective polarization is pointing right or left in this case. And in this region, which is another type of domain, where the magnetization is either up or down, this corresponds to a region in the substrate where the z-axis is either basically in the vertical direction. So this correlates very nicely with the X-ray data and the type of microstructure that we expect. So we can say that we can control the anisotropy with the strain and stress coming from the substrate. So the question is then, can you manipulate this microstructure with an electric field in order to have an electric effects? And the answer is yes. So if you then perform some magnetic studies again, so here what we've done is measure magnetization as a function of angle at different temperatures in the different phases. So phase number 1 in this case is the rhombohedral phase, phase number 2 is the rhombic phase, and phase number 3 is the tetrahedral phase. We've done magnetic imaging, so you can see that you change the microstructure and you change the local magnetic anisotropy. You can also change the type of anisotropy that you have. So the tetrahedral phase, the material is primarily uniaxial overall, when you take it as a whole. And in the other two phases is primarily biaxial. So if we concentrate in this uniaxial phase, which is interesting for magnetoelectrics, what we can do is basically do the same experiment that I showed you before, but in this case applying an electric field. So you see, you start with an orthorhombic phase in the substrate, and you have this very complex magnetic configuration. And then when you apply an electric field of 4 kilovolts per centimeter, you see that you can change the microstructure. And basically, if you do a polar plot of the distribution of the moment, so you see that here, the magnetization is roughly oriented in all directions. So you have this kind of like globular distribution. And then when you apply an electric field, you see the magnetization is rotated and is aligned along this direction, which is kind of like left to right. So it's this kind of gray and purple. So you can actually rotate the magnetization locally with an electric field. And the mechanism, I mean, as we understand it, is that if you start in an orthorhombic phase, where again the polarization is mostly in plane, when you apply an electric field out of plane, because this is the configuration, so we have LSMO, barium titanate, and then an bottom electrode, so electric field is out of plane. When you apply the electric field out of plane, the polarization rotates out of plane. So you are changing the strain that the substrate, that the film is seeing. So initially the substrate is showing this strain configuration to the film. So it's almost a square unit cell. So this is why the material is primarily biaxial, because it can be pointing in all directions. And then when you see the polarization out of plane, the strain template that the substrate is presenting to the film is like a rectangle. And again, when it's a rectangle, the polarization is going to align along the wrong direction. So in this case will be the z-axis. And this is why you have this kind of uniaxial magnetic anisotropy of the electric field. This is consistent with early observations done using only macroscopic magnetization data, where it was reported that when applying field at this temperature, the magnetization was dropping significantly. But notice that this was measured at very small magnetic field, 92 millitesla, which means that the magnetic field was not able to align the magnetization, because otherwise you will not see this big change. You will see really nothing. And the explanation is precisely this: that when you apply an electric field, you can rotate the magnetization 90 degrees in many places. So if you are measuring along this direction, and then you rotate the magnetization 90 degrees, the component that you measure in the magnetometer is going to be much smaller. So this is why you see this. Then what we did is we focus on the room temperature phase. Because the room temperature phase is interesting because the film is closer to the Curie point, so you may expect to change the magnetic properties more dramatically. And also interestingly, the strain changes are very large, associated with the rotation of the polarization with the diagonal phase. So what we did here is we measure again magnetization as a function of field before and after electric field. And you can see again that there is a very big change in magnetization now in this film, which is good because this is going to give us a very large magnetoelectric effect. You can see this using magnetization and magnetometry. You can also see this in ferromagnetic resonance, where initially you have two peaks and then you have only one. And this is pointing to the fact that before applying field, you have two different regions of magnetization in the film. So you have two different resonance peaks. And when you apply the electric field, you convert one of the regions into the other. So this is why these peaks disappear and this peak increases. And I'll tell you in a second why is this. We also did magnetization as a function of temperature measurements in order to see potential changes in the Curie point in this material. And you can actually see, I mean, the data is a bit noisy because the sample, the signal at room temperature is not so intense. But you can see if you compare the black data with the red data, you can see that there is an increase in the Curie point in the film as well when you apply the field. So this is pointing out all this information to the fact that when you apply electric field at room temperature in this system, you can control the Curie point, which is interesting, actually both for magnetoelectric from the magnetoelectric point of view and the caloric point of view. So in order to understand this in detail, what we did is again magnetic microscopy at diamond. And then just if you concentrate on these two bottom images, which are easier to interpret, again, this is a map of the magnitude of the local magnetization. So here, regions that are black means that the magnetization is very small or zero. And the regions that are white are regions where the magnetization is very high. So basically, what you can see is before applying an electric field, so this image, the sample actually is made of two different regions. So regions where the magnetization is very, very small and regions where the magnetization is high, which is consistent with these two resonant peaks. And then when you apply an electric field to the substrate, you see you convert these low magnetization regions into high magnetization regions. So this is why this peak disappears and this peak increases, and then the overall magnetization is increasing. Now, the explanation for this effect again lies with the strain coming from the substrate. So if you remember, these substrates initially in the tetragonal phase have mostly the polarization in plane, and then you have this kind of structure of polarization pointing to the right and then down, to the right, down. So you have this kind of pattern. And when this happens, the strain that the substrate is showing to the film is very large. Because the lattice parameter of LSMO is around 3.86, and the lattice parameter, let's say the C-axis lattice parameter for our entitlement is 4.02. So this is a very big change in strain. And when this happens, because the LSMO is so strained, basically you are changing the distance between the manganese atoms. This changes the exchange interaction between the manganese atoms and decreases the Curie point, and therefore also the magnetization. So what you can expect is that these regions here are regions where the polarization in the substrate is in plane, so the film is very strained and the Curie point is depressed, so the magnetization is small. And then when you apply an electric field, what you do is you switch these domains out of plane. So now the substrate is going to show this square pattern to the film, where the a-axis is smaller, is around 3.996. So the strain change is smaller than before. And then you see that when you do this, you relax the strain in these regions, because the other region remains the same, and then you can increase the break point. And this is interesting because, as I said, it gives you a very large magnetoelectric effect. So you can quantify this using this magnetoelectric coefficient alpha, which is basically the change in ionization divided by the change in electric field. And you can see that actually, I mean, so this graph is comparing this data, which is again data, with the previous data on this material. But this material already was one of the best magnetoelectric systems out there. So you can see that actually at room temperature, you can increase the magnetoelectric coefficient by a big factor, and then obtain what are actually very large magnetoelectric effects in these units. And also interestingly, because you are in effect driving a magnetic transition, right? You're going from, let's say, paramagnetic to ferromagnetic. If you can control the microstructure of this material, you can also have very large caloric effects in the film, in this case driven with an electric field. So this will be an example of a multi-caloric material. Right, okay, so now let me just conclude with another type of study. So now I'm going to focus in on electrostatic pressure on this well-known magnetocaloric compound. And just to remind you, I mean, all of you know about caloric effects. Caloric effects are potentially interesting for cooling applications. They are thermal changes that you can drive in materials when you apply external fields, and the field can be a magnetic field, an electric field, or a mechanical field. So therefore you have magnetocaloric, electrocaloric, and elasto and barocaloric effects depending on the field that you use. And traditionally, the materials that have been investigated the most are magnetocalorics, because they've been investigated now for many decades, and they show potential for efficient applications because you can use permanent magnets to drive these changes. If someone is interested in the room in calorics and they are not familiar with the subject, this is a list of a couple of review papers that have been published, one few years ago, and then a recent one last year in November. And this is covering basically all the different types of caloric effects. So if you look at the different types of caloric effects, they have different advantages and disadvantages. So magnetocaloric materials have the advantage that you use permanent magnets to drive them, so potentially they can be very efficient. But they have the problem that in practice, permanent magnets that you can use in applications are around 1 Tesla, 1.5 Tesla. So the thermal performance of the material is limited, it's quite small under this kind of small magnetic. So that's one of the challenges that you have. Electrocalorics have a different challenge, that is not to break down the samples electrically when they apply a big electric field. And for these reasons, lately, these two types of materials, which together are called mechanocalorics, have been gaining interest. And I will argue that actually barocalorics are really interesting, because in a way they overcome the problems that the other ones have. So if you compare barocalorics with magnetocalorics, actually applying hydrostatic pressure is quite simple. Just need a fluid and a piston. Compared to electrocalorics, you don't really have breakdown in barocalorics, because even if the sample crumbles and it increases, it's going to still work. And compared to elastocalorics, you don't have so much fatigue, because the pressure is hydrostatic, so you can take the sample in a piston and then there's no cancers that you want. So barocalorics are interesting for all these very reasons, and we will tell you a bit more later in this talk. And they are also interesting from the fact that they are also potentially efficient, or quite efficient. So if you calculate what is the energy efficiency of the material itself, so this parameter eta is nothing to do with the device. It's not a cooling cycle. It's just telling you how much heat you can get in and out of a caloric material divided by the amount of work that you do to drive them. You can see that barocalorics are actually up there with the best magnetocaloric system. So these are all very promising. And indeed, there are many good materials out there already. So this is a list. I mean, it's not updated. It's a list of very good magnetocaloric compounds that are also barocaloric. So these compounds basically, I mean, they've been investigated by Luis and Baris as well. So you will hear more about them in the session this morning. And you can see that they have actually what is called a good performance, I mean, a giant performance. So normally an entropy change of around 20 joules per Kelvin kilo is what we call a giant effect in this solid state caloric community. So something that we wanted to investigate is what happens when the materials have very large hysteresis. Because something that is important is that the effect is reversible, because you need to be able to drive it when applying field and then undrive it when you remove the field. And there are some magnetic compounds that are actually not that reversible when they apply a magnetic field. And then here there is, I mean, this is an example of one of them. So this is a barium doped manganese cobalt germanium material. It shows very large magnetically driven entropy changes when they apply 2 Teslas and 4 Teslas. So these are for these two dope compositions. So you can see there is a magnetostructural transition when you change temperature between a paramagnetic hexagonal phase and a paramagnetic orthorhombic phase. There's an increase in ionization. You can vary the field, but because the hysteresis is large, the effect in practice is not reversible. So it's
Excuse me, Xavier. 2 minutes left.
But I will finish in a
Okay.
What we wanted to do is to investigate what happens when you apply pressure instead of heat. Because as I said, the volume changes in these materials are 4%, so these are large. These are very large in a solid material. And this is detrimental for magnetocalorics because the sample will crumble, but it's actually beneficial for barocalorics because actually the heat exchange will be better. So what we did is we synthesized these samples. We did calorimetry as a function of pressure, which is shown here. So you can see that the transition is shifting down. So this is an inverse barocaloric material. And then what you can do is you can do the calculations of caloric effects, and this is a summary of the results. And you can see that actually, because the volume change is so large in this material, the transition shifts a lot with pressure. So you can actually get very large barocaloric effects under relatively small pressures, and they are actually reversible at low pressure. So you can then compare these to the existing materials that I show you. So you can see that the performance is pretty good. And importantly, I guess the message is that you can take sometimes magnetocaloric materials that are actually not reversible, applying magnetic field, because the shift with magnetic field of position is not that large, and then use pressure instead. So I think there are materials out there that can be actually quite interesting for barocalorics, even though for magnetocaloric perhaps are not reversible. And with this, I just conclude. So I show you 3 different examples of how you can take traditional magnetocaloric materials and use stress and strain to get new properties out of them. So for the case of ICMOVTO, you can use a strain to get these extrinsic magnetocaloric effects. For the case of LSMOVTO, you can use these changes in strain to get large magnetoelectric effects. And in the case of the boron-doped manganese cobalt germanium, you can use electrostatic pressure instead of magnetic field in order to get reversible caloric effects. And with that, I thank you for your attention.
Thank you very much.
Nice talk, but it is interesting for me that how it is possible to make isotropic stress, the pressure is a vector.
No, but this is hydrostatic pressure.
So it's all hydraulics. I mean, basically what you do in practice is that you have a sample in a container, and this blue color is a fluid. So what you do is you apply force to the fluid, and then the fluid applies hydrostatic pressure to the sample.